Alright, so I'm going to try to make a video showing my design process and plus a little bit of extra background here and there. So I want to make a motor controller, or I want to have a motor controller for this motor. It is a 12 volt linear actuator, and it doesn't say it on the tin. Let's see here. It doesn't say it on here how much current it wants. But on the actual physical one that I have, it does, and it's 3 amps. But I believe also somewhere around here it tells you, yeah, rated current 3 amps. So I'm going to need some sort of motor controller that can handle 3 amps. I could just have so if we have my little motor here, right? That's my motor, and I'll have a couple wires coming out of it. Alright, so here's my terminal block. I can just take this wire and go boop, and this one and go boop, and then it would just kind of always be on. This is my 12 volt source, ground. And then if I ever want to turn it off, I can just take a wire cutters and just chop it up. But I hope you can imagine that that is kind of error prone. You might short something, like accidentally take power to ground and catch something on fire. It's also very labor intensive, and you can't get good control with it. So all in all, I hope you can see that this is technically possible, but not that great of an option. Another thing I could do is have a switch. I could have a little switch in here. Yeah. And if I want to turn it on, I can just flick the switch. If I want to turn it off, I can flick the switch and it'll turn off. And that'll be a lot more convenient. It's only a single switch to turn it on or off. However, it doesn't. You can't get really good control. You can't move at half speed, for instance. I mean, maybe you could just like really quickly move it back and forth between on and off, many times per second, and like half the time be off and half the time be on. But that's really hard for a human to do. But it's not too hard for a computer to do. So we'll put the switch back in there. There are these things called transistors, and I'll just draw. I'll just draw a switch here. We call it a transistor, and so we'll put 24 volts up here, and we'll put a ground down here. Actually, no, we'll put our motor. That's my motor, and then that means ground. So if I put 24 volts here, then this looks like a short to ground, or a short to our motor, right? And if I don't have voltage on it, then it looks like an open circuit, broken circuit. And electrons will not be able to flow. And these can be, pulsed, turned on and off thousands, or technically even millions of times, if I wanted. And I could turn it on, maybe 75% of the time it'll be on, or 25% of the time it'll be on, or 3% of the time, You can get a lot more control with that. However, the issue with this is that I can find, they're called MOSFETs, or just I can't find a transistor that can handle that current, 3 amps, but I won't be able to run it in reverse. There's an issue with these if you run them backwards. So let me label this. Let me call this an NPN, NMOS, which stands for don't worry about it. Sorry. We call this D for drain, this S for source, don't worry about the things, and then this is G for gate. There's an issue with that. If you put it in backwards, bad things happen. So this will still be gate, but then this is drain, and then this is source. And then call this ground. There's an issue with this. It'll kind of just, I think it'll break or just always stay on. Either way, bad things will happen if you do if you do this. And they cannot be put in backwards. So I cannot run my actuator up and down. So if I turn it on, it'll move up a little piston slowly. And but what I want to be able to do is have it pull the piston back down. But yeah, but the transistor like this is not able to do that. So one of the things that they do is called an H-bridge. Yeah, go down here. H-bridge. Yeah. So if I have something like this, okay. Oop, nope. That says V out. If I can, come on, V out. And this is 24 volts, and we'll just call this ground. So if I tie these two together, okay, if I put 24 volts on this, then this circle means not. So it's called a not gate. Whatever this voltage is, this is not that voltage. If this is on, this is this does not allow current to flow. If this is off, then it allows current to flow. And this one is just a normal one. If this is on, then current may flow. If this is off, then current may not flow. So that's an arrow. So okay, let's try this through. Let's send it. Let's just use digital logic. Let's put a 0 on here. And if this is 0, then this is 0. And if this is a NOT gate, so it's now a 1. It's the opposite. So now this is a 1. And so current can... oh, whoopsies. Come on. Okay, it's just there permanently, yeah. And current may flow like this and put a voltage onto here. And so the output is a 1. If I go through and I put a 1 here, then this is a 1 and this is a 1, but this inverts it, so now it's a 0. So this is a 0. So current may not flow, it gets stopped here, and current is allowed to flow like this. And so the voltage here gets brought down to 0, so it's 0 volts, or logic 0. And that's really wonderful, because we can put another one on the other side. So we have, let me just redraw it. No, I should leave it. Well, whoopsies. Yeah, we'll draw it over here. And my cursor's stuck. There we go. So if we have logic 1 up here, so we're just going to put 1 on the other side. Oh, that is just disgusting, but forgive me. Alright, so we have the NOT gates up here. Or not the NOT gate, but the inverting. Oh, these are not inverting. Alright, and then tie these two together. See if I can scooch over a bit. Alright, so, and this is ground. So we have two different inputs. We have an input over here, and we have an input over here. And then we'll put our motor in here. So if I put voltage, am I still recording? That would be wonderful to know. I am. Wunderbar. Alright. So if I put a 0 here and a 0 here, then just like before, this will be 0, this will be 0, and then this will be 1, this will be 1. So current will be allowed to flow and then get stopped here. Current will be allowed to flow and get stopped here. Current's trying to flow in both directions. So actually, there's just voltage on this line. There's logic 1 here and logic 1 here. There's a difference of 0, so there's no flow. Like if I had one fist, yeah, that's my fist, and I had another fist, and they're pushing up against each other, there's no movement. They can push as hard as they want, but they're not going to move. But if I put a smaller fist, that's a fist, then the stronger fist will win, and it will overall move in that direction. So there has to be a difference of voltage in order for work to be able to be gotten out of it. But since they're both 1 volts, or logic 1, nothing's going to happen. But let's see what happens if I change it. What if I make this one 1? Well then, just as before, this will be turned off, and this will be turned on. And so current will actually be able to flow like this. So this is on, this is off, this is on, this is on. So current will be able to flow, let me draw that again. It'll be able to flow through this one. It will not be able to flow through this one. It'll go through the motor and through this other transistor and then down to ground. And so that's our current path. So in this direction, so in this case, current is flowing in that way. And what's nice about this is if we change that, so now it's 0 over here and 1 over here, then this one turns off, this one turns off, and now current can flow like this. And now current's going in this direction. So we now have the ability to control whether current is going in this direction or current is going in this direction. And that will allow us to turn our motor. So we can have the motor, ooh, I can probably grab this. Wow. We can have the motor go down, or we can have the motor go up. And so that is the basics of an H-bridge, or a what is it called, a bidirectional motor driver. And one of the motor drivers that I was looking at, and it's a very popular one, if I can find it. Here it is. Yep. Yep. Is this one here. And it can handle 3 amps. So this is a LN298. So let me look that up for you, actually. LN298 data sheet. I want the data sheet for it. I don't think this is it. Oh, it is. Okay. So it can handle up to 46 volts. Wonderful. I only need 12. And it can handle up to 4 amps continuous current. And there's a bit more detail on that here. The absolute maximum is 50 volts. Not really safe for it to be run at that. Peak output current. Oh, it's only 3 amps for a single channel. Either way, it doesn't matter. It's not really... I don't really like it because it's not very efficient. It's old. Let's see. There's a date on here. January 2000. It says old. It's older than I am. I like it. It's January. I love this. But it has a, I think like a 1 to 2 volt voltage drop across it, because it's based on some older technology. But it's not very efficient. If you just look at the picture, you see that you see this black thing on the back? That's a gigantic heatsink because it gets so hot and needs to cool down. So they strap a big hunk of metal to it to help cool it down. Yeah, you can see from this perspective, it's mostly that big chunk of metal. And it uses a technology called BJT, bipolar junction transistor. But in my opinion, a decent way to describe the difference between that and modern day MOSFETs is if we have a car on asphalt. Okay, here's a drawing of a car. Yes, a beautiful car. Imagine if instead of having wheels, you just had a sled, and then you pulled it by the sled, and you pulled really hard. That's you. And those are your legs. There you go. You're pulling really, really hard to move this thing on a sled while it's on asphalt. That's like a BJT. There's a lot of friction involved, but it's a lot better than just trying to scrape it against on bare metal. At least you have a sled underneath. but a modern BJT is where you're just doing it on wheels. So it would be, there we go. So you're just trying to pull it while it's on wheels. A lot easier to do. A lot less friction. More efficient in overall. And that's not the best explanation, but it gets the point across. In my opinion. So, I don't want to use that one. I've been looking all around Amazon, different sellers, to just try to find a pre-built module. So I don't have to build one myself. So I can be able to control these. And I'm going to be controlling quite a few different things with it. Not just the one motor, but things in the future I'd like to use. And I don't really see anything that does what I want. I see really expensive, really big ones. But they're way too big for what I'm wanting, and they cost a lot of money. I would rather have a much smaller one that only costs a little bit of money, right? Maybe even just just a really small amount of money, really small footprint, cheap, efficient. I want that kind of stuff, but I have not been able to find it. I've been looking all around. I just can't see them. So, I'm going to build one. I've done similar things with a stepper motor, which is a bit more complicated. But I used this thing here called the wonderful name of DMHC 3025. Very, very nice name, isn't it? But I love this little chip. It's let's see if we can find the specs. It can handle 4 amps max. Don't worry that it's a negative, just 4 amps continuous, and up to 30 volts, which is wonderful. And here's that diagram that I was drawing earlier. It just shows you how the different pins are connected and stuff. So I'm going to go ahead and try to show you my design process for. I have not designed it yet, but I'm going to show you my design process for how I would design it. And this is where my notes stop. I had to say figure it out from here. So it's going to be candid from this point on. So, other considerations about an H-bridge that they've taken care of. If I have a hammer, oh, beautiful hammer, right? If I have a hammer and I have a big bar of just like steel, anvil, we'll call it an anvil. See if I can draw an anvil. Beautiful anvil. If I have a hammer and I invest energy into it, and I invest energy into it, and I invest energy into it, and then bam, I suddenly stop it. There is a really, really high force that goes in the opposite direction. Because if there wasn't a high force, it would just continue to pass through it. There has to be something to push it back. Oh, I wonder, can I? Bang, right? There'd be a really, really high force for a split second. But I can invest energy, and then bang, I'll get a lot of stuff out of it, a lot of force. But that force can be damaging. For instance, if this was a glass hammer, then whenever it hit something, it would just shatter, right? So there's an issue with inductors. That's what these things are called. It's called an inductor. But it's basically there's inductors everywhere. But the motor is especially an inductor, because once you get it spinning, it doesn't want to stop spinning, right? And there's electrons that are in here. that once you get them moving, they don't want to stop moving. Just like a car, once you get it moving, it doesn't want to stop moving. Um, and with our switch analogy, right? If I have a lot of current going, and then I suddenly turn it off, then all of this current has to stop instantly. It just goes boom, and all the electrons get squashed up together, right? And they all get squashed together, and you have really, really high voltage that wants to jump this gap. So there's only a few electrons down here. There's a lot of them up here. They want to jump that gap. And just like when the hammer smacks into this thing, it can cause a high voltage, high force, and it can break things. We can also actually break things by doing this. So what we actually have is called a flyback. There we go. Flyback. So if we ever do turn it off, although actually the electrons will actually be packing up here, but that doesn't matter. If it ever wants to continue to have flow, it will allow a path back. So it'd be like a flywheel on your vehicle. It allows it to continue spinning, and it just disappeared. Okay, I smell gas. Let me go find out what's going on upstairs. Nope, they're just doing some cooking. And there's a flame, so there's not gas leaking into my lungs. Alright, so yeah, it'll allow it to feed back in on itself. And yeah, so you won't get such a high force when you turn it off. So flyback diode, very important. But as you can tell, it's already incorporated into these. So there's a flyback diode right here. If you turn it off and there's ever a really high voltage spike, instead of damaging anything, you just allow it to cycle through itself. So oh, also another thing, these, if we're working at 5 volts, okay, the brains that I'm going to use to control these transistors uses 5 volt logic. So a 0 corresponds to 0 volts, and a 1 corresponds to 5 volts. However, the MOSFETs that I'm going to use, the voltage is depends on what this voltage is. So if this voltage is 12 volts, then it's a 12 volt logic system. So 0 is 0 volts, and 1 goes to 12 volts. But there's an issue. If we try to turn off this guy with 5 volts, and we have 12 volts up here, and it's a 12 volt system, then, and remember, because of the circle here, he only turns off whenever this is a logic 1. So instead of a logic 1, it's more like a logic 0.5. Although it's a bit different than that, but it's not 1. So it's actually, it looks more like a 0 than anything else. And so it'll just always be on and cause issues. But this is only for the turning off ones. For the other ones, called NMOS, or so this is PMOS. This is NMOS. For NMOS, if I put in a 5 volts, It actually equals the logic 1 for the PMOS. And for the PMOS, yeah, just don't worry about it. This will look like logic 1. So if we have it set up like this, then current, there we go. Current will just go straight from 24 volts. It'll just short all the way through, and everything will get really hot really quickly and melt and catch on fire, one of the two. And bad things will happen. So it's very important that we solve this issue. We figure out how to get 12 volt. Sorry, it's not 24 volts. I'm sorry, I've been saying 24. It's 12 volts. Very important that we do not have that happen. So there's a trick that we can do. It's called, so if I'll just give the analogy. If I have a big, infinitely big bucket of water, right? Okay, there's water in here, right? And I have a little spigot coming out of this bucket, and there's a little handle on it. Yeah, there we go. And yeah, I have a little paddle wheel. There. We can spin the paddle wheel. So if I poke a tiny hole in this big bucket of water, then there'll be little drips of water that come down, and I'll get just a little bit of water. Right? And I can eventually fill this thing up. Right? And there'll be a voltage on this thing. Actually, we don't care about voltage. This thing's not voltage controlled. We'll just poke a tiny hole in here, and this will fill up, and we'll get a voltage. But actually, no, I do want this spigot, but I don't want the paddle wheel. But if I open the valve, then I can flush a lot of water out quickly, and we'll lose a lot of water very quickly. There'll still be a little bit of water dripping down, but we can dump water way faster than this tiny trickle can give. If there's a problem, if this is a really, really big hole, then we'll get a lot of water, and this won't be able to stop it. But that's not our issue. We have a tiny, whoopsies, pop. We have a tiny hole, and so we'll slowly fill it up. And if we want, we can open this tap, and a lot of water will come out. So, and it's not going to, because we can dump so much more water through here, the water will not build up if the tap is open. So what we can do is have on our 12 volt rail. So this resistor it's just a resistance. It's a tiny hole. If this is if it's a 10,000 ohm resistor, that's like a tiny hole. If this is a 1 ohm resistor, that is like a really big hole, right? But since it's a 10k ohm resistor, it's a tiny hole. And then we use that to command a there we go. No. There. So now we have to. I'll just. We'll ignore this part for now. So if Whoops, I put this on the wrong side. There we go. That's where it belongs. 10k ohms, 10,000 ohms. If this is off, if we put a 0 here, then this is off. And so this current is allowed to come in here and very slowly, or actually very quickly, actually, but bring the voltage up. So the voltage will go up. Very quickly. I say slowly, but it's very quickly. It's like on the order of like nanoseconds, probably. But it's a very weak source of voltage. But if we come through and make this a 1, then that current has a much better place to go, and it goes straight to ground. And so the voltage here will be 0, which is enough to register a 0. But if we turn it on to a 1, then that's, or if we set this back to 0, then this can be 12 volts, and that will successfully turn off this one. So now we have a way to turn on and off. I don't know why it disappeared. We have a way to turn on and off PMOS transistors, the ones that invert. So the way the circuit is going to look is like this is just a beautiful drawing. I'm sure you can tell. 12 volts. So these are our, this is called, by the way, what we call this is a pull-up resistor. If it was going down, to ground, then we would call it a pull down, because it's pulling up the voltage or it's pulling down the voltage. But it's a very weak, resistor, or very weak source of current, just so that we can bias it one way or another. So that'll go up to 12 volts. Okay, and this is ground. Oop, whoopsies, that's not right. What am I doing? That goes to ground. I believe that this is correct. So these are our two inputs. This, by the way, is called a NOT gate. NOT. And it inverts the signal. So if there's a 1 over here, makes it a, or if there's a 0 over here, makes it a 1. If it's a 1, makes it a 0. So if it was on, now it's off. If it was off, now it's on. So let's run through it. Let's put a 0 here. Then this gets inverted, so now it's a 1. And if this is a 0, then this is off. So current is allowed to flow in. So this becomes a 1. And so this turns off. And let's put a 0 over here. And we'll actually get the same thing. So this will be off. So it winds up becoming 0 volts here and 0 volts here. So now if I undo those changes, actually it might be easier to just spam this. Yeah. Okay, now if I put a 1 here and a 0 here, then this gets inverted. Now it's a 0. Here we go. There we go. If I put a 1 here and a 0 here, then it comes through. Now this is a 0. This is a 1. So now current goes down like that. So there's 0 volts up here. So this is a 0. So then this turns on. This turns off. This one is still on. This one's off. And so current will go this way through the, oopsies, this way through the motor. And if we invert it, There we go. Put a 0 over here and a 1 over here. Then this is a 0. Current goes in like this. This turns off. Wait a minute. I might have told you wrong. Am I just confused? Hang on. If this is a 1, and this turns on, current gets shorted. This turns off. Stays on, sorry. This is 0 volts here, so it stays on. There we go. 0. So that stays on. 0, this becomes a 1, and this turns off, so this becomes a 1, and so current will go, sorry, this is a 1, so then this turns off, sorry, I'm confusing myself, and then current can go this way, and so now we can send current this way or this way through our motor. And now that I'm looking at it, I might be able to get away with just this here. So let me redraw what I'm thinking here. I might be able to do might be able to just do that. See if that's okay. So if I put a 0 here, and by the way, in more detail about these turn off, these go from, I'll draw it up here. So NMOS. And the specific one in the datasheet, we can look at it. We can look at the datasheet. Let's do that. Blinded. Maximum ratings. I'm looking for electrical characteristics. Okay, breakdown voltage. Gate threshold voltage for N channel, so NMOS. Gate threshold voltage. This might not be what I'm looking for. It wouldn't be from 1 to 2 volts. Okay, yeah, let's go with that. Okay, let's say worst case scenario, 2 volts. This thing turns off, completely closes up at 0 volts. We'll say that. And it completely turns on at 2 volts. It's not exactly 0 volts, but it's close enough. And it turns on completely at 2 volts. For the PMOS, or P channel, it turns off fighting my, there we go, P channel, gate threshold, and it's a negative, but it's also the same, negative 2 volts. So this one, so VGS, I believe it called it. VGS. Okay, let's look up. Let me just show you. This is don't worry about these backgrounds. They're random every single time, and I like them. Like that one's kind of pretty right there. Let's look it up. It is. I'm going to show you PMOS. Yeah, I think this is what I'm looking for. That's not what I'm looking for. I halfway there. There we go. That's what I'm looking for. Ah, it's so small. All right. Nope, I still can't see. Okay, that's better. All right. Whoa. It's a bunch of different symbols here. We have NMOS. We have drain, gate, source. So that's how it's normally drawn. Gain on top, drain, source. So this is called the gate. This is gate, drain on top, source on bottom. And then this one, it's backwards. It is why did they? That nobody draws it. Okay, going back. So if you don't draw the things, it's a pain. This is how real people draw them. We have the arrow is always on the source side. Yeah, and all of these voltages are relative between G and S. So in this case, it's positive 2 or positive 0. So this is off if the voltage between here and here are the same, then this thing turns off. And this one turns off at negative 0 and negative 2. So if the voltage between here and here are negative 2, going in this direction, then it turns on. So if this voltage is 10 volts, 12 volts, then this voltage must be 10 volts in order for it to be completely turned off. Well, let's actually backwards. Sorry. On, off. For it to be completely turned off, that voltage must be like that. For it to be completely turned on, then this needs to be 12, and this also needs to be 12. Although it's not quite like that. Just bear with me. So I think this would be okay. So if this voltage is 0 and 12, that's okay. 0 and 0, that's okay. So I think this would be okay to have. So if I put a 0 here, this would turn off. Current would be able to come in, raise the voltage. This is 1 and 1. And if they're both 1 volt, or logic 1, then this one's off. Sorry, I'm confusing myself. There we go. Oh yeah, I did have that. Hang on. There. Yes, this one turns off and this one turns on, and so that's what we want, because we'll have 12 volts here, 12 volts here, and if I put a 1 here, then I'll erase my entire thing. Okay, then current will be allowed to flow. It's not going to come here. Voltage here is going to be 0. Yeah. And so 0. So this will be allowed to flow. That'll be turned off. Yeah. Okay. I'll do that. Saves me a whole component. So that way I only need 2 of these guys. All right. Okay. Now let's look at the pinout of our DMHC. So draw all of the legs. Okay. So this is P1G, so that's the PMOS gate 1. This entire side is called 1, and this entire side is called 2. So this is P1G, so that's right here. So, they call this right here, they call this P1G. And they call this bottom one N1G. So what I'm going to do is connect both of these. This is N1G. Come on. Close enough. And this is P1S, P2S, which is up here. This is our power source. So we're going to call this VDD. That's a pretty common way of calling power. Right? This one is N2D, P2D. This one here. So this is output. So we'll call this output. We'll call this output A, and we'll call the right-hand side output B. So we'll call this output B. And so this one here is P2G, and that's this one here, P2G, and also the one on bottom, N1G. So I want to connect these two together. Yeah, this is... And there's also other stuff that happens here. I'm just not drawing it. Okay, N1D, P1D. So that's this one here. This is our output A. And N1S. Okay, so that's ground. We're gonna call that ground. Alright, now I need to find myself a NMOS transistor. Okay, I have to search for specifically DigiKey. Wonderful place to buy stuff. Products. Whoa. Transistors. I see. Oh, semiconductors. Okay. Discrete? Transistors, bipolar BJT. That's the old stuff. Transistors, MOSFETs, single. Yeah. Oh, by the way, IGBT and JFET is for like high power, I believe. But I'm wanting a logic. Not much current. This guy here doesn't have to draw much current at all. For instance, if let me go through the equation. I'll do the equation down here. So if I have the equation for current is I, which is what we call current. Don't ask why. I equals V divided by R, voltage divided by resistance. And this relation should make sense. The harder you push, the faster you go. The rougher the ground, the slower you go. That should make sense. Like if you have old tires and they're popped and you're driving through sand, really rough stuff, and you're not pushing very hard, then don't expect to go very far or to be going very fast. So if I have 12 volts and 10k ohms, that is 10,000, 1.2 milliamps. 1.2 milliamps. That's not a lot of current. That's easy to get rid of. For instance, this guy here, he's going to have to be dumping 3 amps. It can even do all the way up to 4. Or, this is kind of cool, in short spurts, it can do... I'm right at the top. In short spurts, it can do Maximum ratings. Pulsed drain, 1% duty cycle. It can do 60 amps for a very short amount of time, which is pretty cool. But yeah, so that's like 3,000 times more. Why is it showing an eraser? But it was drawing. That was strange. Alright. It's stuck on the eraser. Get off the eraser. Alright. There we go. That's like 3,000 times. So a milliamp is a thousandth of an amp. So if it can dump 3 amps, and I'm only wanting to do 1 milliamp, that's like 3,000 times less current to worry about. So I can find a pretty tiny transistor. All right, so this one cost 15 cents. Let's take a look at it. Data sheet. It's 15 cents if you buy one. If you buy 1,000 of them, it's only 3 cents. All right, so it can this is NMOS? Yeah, N channel. It can handle 60 volts. Okay, we're good on that. It can put 20 volts onto the gate source. That's fine. We're only going to put 12. Actually, no. My microcontroller is only going to put 5, or possibly even only 3. Speaking of which, I don't think I bought one. I need to buy one. Well, I'd rather not dox myself. I'll buy that later. Yep, 300 milliamps, plenty. We only need 1.2. And that's pretty much all the information I need. I can get package sizes later, but yeah. So I'll probably wind up using something similar to this, although I might search it up later. So, yeah. And then I'm going to want a transistor on each side. I also need a resistor, so I need a we'll call this control. We'll call this in A. In one. We'll call it in one. In two, because they don't directly relate to them. But well, yeah, we'll call it in A. In B. All right. And then down, I want to have a this is just my microcontroller. Or no, this is going to be an individual board, right? So I'm going to have terminal blocks for in A. There we go. And then that will go to a train of thought transistor. Oh, and a resistor. Okay, so we have 12 volts. And then another one for B. We'll just make a new 12. All right. And this is going out. We'll just call this A. Yeah. There. Name your nodes. So we have A, in A, and B. You know what? I'm going to change the name. Go to call an audible. I'm going to call that A, call this B. And we'll call this in A and in B. So then you can just be A, and you can just be B. 10K, 10K, just so I don't forget. All right. That's probably all I want. So let me... Okay, let me go to sign in. Don't want to dox myself. This is a Chinese, very Chinese website. But it's okay. I want to make a new project. Let's call this... so I've already made a motor driver. I just want to differentiate. This is not a stepper motor driver. It's DC motor driver. Save. Alright. Okay, so now we need to draw some stuff. I want my DMCH. It might be better to go to LCSC. No, I think they do it in here. Yeah, here we are. Okay, so DMHC or CH? Let's search. Not what I'm looking for. Here it is. DMHC. 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 Okay, so 3025. Wonderful. Place. And I'm going to want just one of these. It's just a single motor driver. Yeah. And W for wire. I want to connect these two together. And this is just a cosmetic, mostly cosmetic thing for me. It'll create a nut list, which is the actual top of what? Is this not connected? There we go. This is just to make a schematic for the nut list to be made. Technically, you don't need this, but it helps with some design, and it's good practice. So I just want one of these, and I want some terminal blocks. Can I just search terminal block? I don't know. Terminal block. What I'm trying to find is where's that window? Here it is. You see these blue things that you can stick a wire into and screw down on? That's a terminal block. Although these look like really cheap ones. I don't know if I'd like that too much. Yeah. Okay, there are no pictures on these, which is concerning. Oh, I'm probably going to have to solder that on myself. Bleh. Put a digikey. Oop, that's not what I wanted. Terminal block. Here we go. CK. Yeah, wire to board. I only need 4. I need 4. I need 1 for power, 1 for ground, and then 1 for A and B. Ooh, should I make it more complicated than that? So, should I have power, ground, A, B? Or should I have some sort of command, some sort of communication terminal? And then probably a clock as well. And then have brains. That's a brain, by the way. Have a brain that automatically commands A and B. I think I'm leaning towards this, and have the brains that command it be a separate thing. Yeah. Ooh. I'm gonna have to think about that. I might have to pause the recording and think about that. Because if I have this, then on my microcontroller, for every single motor that I want, I'm going to have to command. I'm going to have to command each one of these with like a PWM thing. I'm going to run out of pins eventually. I will eventually run out of pins, so I can't control too many. But if I have it built into it, to where you communicate to it over, I don't know, magic. I'll just say magic. And you tell this thing, hey, I want you to deal with the controlling of this. I just want you to set it to 50%. Because then I can also include like an e-stop or something into this that tells this thing, no. I want e-stop to happen to kill this. But I could have e-stop stands for emergency stop, by the way. So it's like something goes wrong, we just kill power. This thing doesn't even have the chance to make a mistake. But I could have a command out for error. Yeah. And if anything goes wrong, I can feed this back out and kill power to everything. The reason why I want this is because this isn't going to be the only motor. Let's say I have a table that I want to remain flat. And I have one motor here and another motor here. And if they're both lifting at the same speed, that's fine. But if one of them loses power and it just stops, right? But the other one just keeps going, then you'll twist the table and, I don't know, maybe break the table, snap it right there in the middle. So I'm not sure what that will do. So like instead of having a perfectly flat table with nice 90-degree corners, you'll wind up with with not 90-degree corners, and you'll probably break something in the middle, is my guess. But we could have... We could have error on this. Should we have detection on this one? Interesting. I'm going to have to think about this for a bit.